This is the third and final video on using the PV and TV diagrams, in particular with the VaporDome, phase change substances, problem solving and using those diagrams to your advantage in problem solving. And this has to do with a student asking in one of the Zoom meetings, what's the shape of an isobar? What's the shape mathematically of an isotherm? And that turns out to be a very good and insightful question. And so I want to just give you a little background on how do we determine mathematically what the shape of an isotherm and an isobar is. So let's go ahead and get started. So this one's going to address the shape, sort of the mathematical equation, or at least shape, of isobars and isotherms on PV and TV diagrams. And the purpose of this primarily is, back in part one, I said, trust me on this, I'm just going to have to ask you to memorize what an isotherm looks like on a PV diagram. And I'm just going to have to ask you to memorize what a isobar looks like on a TV diagram. And then I just went on from there. So this part three has to do with going back. Now that you're more comfortable with problem solving, dive down a little bit more into the mathematical relationships. I think this can have a lot of value for those folks that are contemplating maybe going to graduate school. It's these type of subtle type things that we address at the graduate level. So here's what you're going to need for a full understanding of what I'm going to cover here. One is you're going to need to have a basic understanding of ideal gas substances. So this set of three videos is talking a lot about phase change substances. The VaporDome put onto PV and TV diagrams. In your class, it is my hope that you've also covered the type of substances that we're calling ideal gases, things that you kind of recognize as a commonly found gas: air, nitrogen, carbon dioxide, argon. These are substances that typically you're going to say, when I read that in a problem, when I encounter these substances in engineering, I'm going to treat them as ideal gases. You need to have a basic understanding also of phase change substances like H2O, water and steam, refrigerant, propane, ammonia can change phases. So I hope that you have an understanding of those phases of those types of substances. And then finally, expect you to have a basic understanding of PV and TV diagrams, particularly when we're drawing in vapor domes and dealing with problems where the phase of the substance is changing, maybe from saturated liquid, from under the dome all the way out to superheated vapor, something like that, or back in the other direction. So now let's switch gears a little bit and talk about ideal gases. Let's talk about what you know about an ideal gas. When I say the word ideal gas, it is my hope that two things pop into your mind without going to a formula sheet. And that's the ideal gas equation of state. P times little v equals RT. Okay. Now, somebody say, well, that doesn't look too familiar, but I do remember PV equals MRT. That absolutely is true for a closed system. And so remember that capital V divided by M is little v. So typically, if we reduce it down to the most simple, P times little v equals RT. And also you remember, what's R for an ideal gas? For any ideal gas, R, the gas constant, is simply defined as R bar over the molecular weight. And R bar is the universal gas constant that, if you don't know it by heart, you can look it up in the back of your book in the conversion factors page. So R, the gas constant, is a constant number for an ideal gas. So what I want to cover now, so this is What's the shape of an isotherm on a PV diagram for ideal gases? So think back about video number 1 where I was kind of drawing this crazy dog leg line for an isotherm on PV. Let's just look at an isotherm on a PV diagram for an ideal gas. Forget the vapor dome. Ideal gas. So let's see, what is an isotherm in the first place? It's a line of constant temperature. You've got that now. Isotherm, constant temperature. On a TV diagram, an isotherm is just a horizontal line, isn't it? That's easy. For an ideal gas, on a TV diagram, isotherm, horizontal line. T is constant. Now, so let's look at our ideal gas equation state. PV equals RT. Okay. For an isotherm, let's look at the right-hand side of that equation for a constant temperature. For an isotherm, R, constant. If T is constant, the right-hand side would be constant. Okay. So on a PV diagram, where P is on the Y and V is on the X, an isotherm follows the function PV equals RT equals constant. Okay. Solve for P, the y-axis. P is RT divided by V, or in other words, P is V to the -1 times a constant, RT. So what does that mean? What does that mean mathematically? That means on a pressure volume diagram, the shape of an isotherm is a hyperbola. You covered this in high school. Y equals constant divided by X. That's a hyperbola. Oh, I think I remember that from high school. Great. Okay, you're going to depend on knowing that now. So what does that look like graphically? For ideal gases, a pressure volume diagram, a PV diagram for ideal gases, I've drawn in 1, 2, 3, 4, 5 hyperbolas of different temperatures. So I drew in one, just called it T1 equals some number. T1 is, I don't know, 300 degrees K. T2 is a little bigger than 300 degrees K. T3 is bigger. So you can satisfy yourself that mathematically, isotherms represent a family of hyperbolas on a PV diagram. So now that could come really handy for problems that fall into the ideal gas category in this class. So that's kind of like a little extra I'm giving you. So isothermal processes for ideal gases are hyperbolas, and those are easy to integrate, So remember on a PV diagram, what you were integrating things on a PV diagram. Work is the integral of PDV. So just put that in the back of your head. Isotherms, PV diagram are hyperbolas, and they're easy to integrate mathematically. Okay, that's a big takeaway. That's one of my big deals for the video here. Next is, what's the shape of an isobar on TV diagrams for ideal gases? Let's only talk about ideal gases now. Well, what's an isobar? Isobar, line of constant pressure. I droned on and on in the first video about that dog leg line for under the dome, but we've got an ideal gas. So we're not going to worry about a vapor dome for an ideal gas. Okay. On a PV diagram for an ideal gas, an isobar is a horizontal line. P is constant. Okay, horizontal line. Okay. Let's do that same drill. Let's see what we get using that same drill with the ideal gas equation of state. P times little v equals RT for an isobar. Well, let's see. Let's solve for T. Okay, and you see I'm flipping things over. Let's solve for T. And so T is going to be equal to PV divided by R. I just flipped the left-hand side and the right-hand side. Okay, so for an isobar, a line of constant, isobar, line of constant pressure, T, the y-axis on a TV diagram, T is equal to P over R, a constant, times V. That's like the X. That's like X. Let's study on this. Boy, from the 5th grade, Y equals mx plus B. You got that nailed. Slope, M, P over R. B, intercept, 0. Okay. So T is equal to some slope, P over R, times V. Okay, wow. Okay, so that's like Y. So in other words, on a TV diagram, the shape of an isotherm is a straight line passing through the origin, B equals 0. Let's see what that looks like. Okay, so here's my TV diagram for an ideal gas. I've drawn in 1, 2, 3, 4, 5 lines of constant pressure. I started out at P1 equals some low number. Okay, P is some low number. And as we increase the pressure, all we do is increase the slope of the line. Okay, and so this is our family. So it's kind of easy to remember. So isobars on a TV diagram, lines of constant pressure on a TV diagram for ideal gases, is simply a family of straight lines with pressure increasing, fanning out, all headed towards the origin. Huh. Okay. That's kind of another big conclusion. So now what I want to do, now I'm going to drift away from pure mathematics and talk about sort of an analogy, okay? Because so let's look at let's apply what we just learned or what I just demonstrated to phase change substances. And why am I going through this? That is because students are going to say, how do I remember the shape of an isotherm on a PV vapor dome? And how do I remember the shape of an isobar on a TV vapor dome? I ask you to just memorize that and move ahead, okay? But now we can apply sort of what we learned for this ideal gas, analogize that to the vapor dome. So here we go. So the first question is, where does an ideal gas fit on a phase change vapor dome? So for example, nitrogen. You know that nitrogen can exist as a liquid. We've seen those cooking shows where somebody dips fruit down in nitrogen, in liquid nitrogen bottle, and you get some fabulous dessert or something like that. So we know liquid nitrogen exists. So nitrogen typically an ideal gas at ambient temperature and pressure, but if you really cool it down, it can become a liquid. So where do ideal gases fall sort of in the whole scheme of the PV diagram? And I'm trying to depict, here's where it is. So I've sort of drawn in some vapor dome. And here's the critical point. So this is the region where ideal gas, if this was H2O, can you think, you know where this would be out in the superheated vapor phase, wouldn't it? But so we're way out here in the superheated vapor phase, way out in specific volume, way down below the critical point. So the big thing here, the region of ideal gas behavior is where the temperature of the gas is much, much greater than T critical, and the pressure is much, much less than the critical pressure. Okay, so here's my yellow. Using the isobar and isotherm shapes that we just talked about, let's see how we can apply that to getting closer and closer and closer to the vapor dome. Okay, that's the idea here. Ideal gases certainly do fit on a continuum of substances, and we also realize that for things like nitrogen, there is a critical point associated with nitrogen, and you get it much, much really, really cold. You can get liquid nitrogen, so you can deal under the dome with liquid nitrogen as well. Okay, so much for that. So isotherm. So here's my kind of big takeaway. I suggested you memorize the shape of these isotherms. Just put it in your mind. Starts out high, swoops down until it hits the vapor dome. Then it becomes a horizontal line because P and T, temperature, isotherm, are dependent properties under the dome. So it's got to be horizontal. And so my big takeaway is these swooping down lines to the right of the vapor dome are hyperbolic in shape. They're curved lines, they're hyperbolic, and this also helps show that we start out T1 as some number, a higher temperature isotherm is above that, and a higher temperature isotherm is above that. And so that's a little bit of my big takeaway for this video is I want to communicate mathematically. You can show that these dogleg lines for isotherms on the PV diagram are hyperbolas when you're not underneath the vapor dome. Okay, that's sort of my big takeaway. Here's the next big takeaway for a temperature volume diagram. Remember, isobars, lines of constant pressure. Under the dome, they're horizontal lines because P and T are dependent properties. But look, once you start penetrating, once you get to the right of the vapor dome, these lines of constant pressure are straight lines, but they are they are not parallel with each other. They are diverging from one another. And there are some really neat and subtle benefits, some physical benefits to these pressure lines diverging as you go bigger in specific volume. Won't get into it. That's going to be for another day when you start studying the behavior of jet engines a little later in the course and also in graduate school. So anyway, big takeaway here is isobars on the TV vapor dome are basically straight lines that are diverging. Okay, big takeaway. So you may say, so what? This doesn't have anything to do with the homework. That is quite true. And so that's why this is going to be a little bit of a short video. Don't have any example problems to demonstrate. But my hope on this third video was to give you a way to help remember what's the shape of a isotherm on a PV diagram and what's the shape of a isobar on a TV diagram. Okay, so here's the big takeaway. On the PV diagram, isotherms are a family of hyperbolas, except under the dome, horizontal. On the TV diagram, isobars are straight lines passing through the origin that are diverging, except under the dome, where they're horizontal lines. Okay, that is it. I hope that you hung in there to listen to that discussion. If you didn't follow it, it's really no big deal. That's okay. You're still going to make out just fine as long as you're really up to speed on videos number 1 and videos number 2 in terms of letting the PV and TV diagram and vapor dome be your friend and help you in problem solving. They're going to be incredibly important when you're taking quizzes and tests and the final exam. So really want to encourage you to spend plenty of time, plenty of repetition, problem solving, phase change substances using the PV and TV diagrams.